Hey everybody, we're going to spend a little bit of time talking about kinetics. This video will introduce kinetics and some of the concepts behind it, and some of the chemistry behind what kinetics is. Now here you'll see that I say that we're traveling at the speed of chemistry. Up until this point in chemistry, you probably haven't seen anything that had to do with time, how fast a reaction takes. And kinetics is the study of time in a reaction. So the example that I always use is, does carbon, or graphite get turned into diamonds? Is that a spontaneous process? Yeah, it is under the right amount of pressure. But how come if I take a lump of coal out and put it right here in front of the camera, how come it's not going to turn into diamond right in front of the camera? It's because it takes a lot of time to do that. So millions of years. So kinetics is the study of the rate or how fast the reaction is going. Okay, so that's what I have here. I also kind of made this PowerPoint a little more outliney. Maybe it's easier to take some notes and things like that. But so again, kinetics is the rate at which the reaction occurs here. If you see that. Oh, let's go back here. Let me make sure that I have my marker on. Okay. And so it talks about how fast the reaction is going. What is the rate of the chemical reaction? That's the question that it answers. Also, kind of the last part of this unit is going to deal with the pathway or the mechanism. Realize that we've only really talked about reactants and products in chemistry. We haven't talked about what happens to go from reactants to products. And so kinetics can address some of the in-between stuff that happens when we go from reactants to products in a chemical reaction. So a rate, no matter what you're measuring the rate of, is the change in something over the change in time, okay? And so for a rate of a reaction, it's how the concentration changes over time. Keep in mind that this capital Greek letter delta always means change in, and then it's a change in whatever happens to be here. And so this change is a change in the concentration over time. Okay, over the change in time. And so all we have to do is keep in mind that concentration is a measure of how much reactants and how much products there are whenever we're talking about it. So at whatever time we're talking about the reaction. So if we think about the reactants, what happens to the reactants over the course of a reaction? The amount of the reactants decreases, it goes down. So this concentration here is going to change. It's going to decrease over time. So we get a change in the concentration over time. Okay, and so just like it says here, we measure concentration in that unit molarity, which molarity is moles per liter. Okay, something that you're going to want to keep in mind. And then here, time. Okay, while in the past we may have been concerned with getting to base units, in this case we can measure time using any unit of time as long as it is consistent through the problem. And in this case we're going to keep it consistent through the problem. If we are given a time in hours, the whole problem is going to deal with hours. If we're given a time in seconds, we're going to keep it in seconds. Years, those are kind of the three basic ones, although I have seen problems that require, instead of, they may use months or minutes or something like that. But typically, as long as the unit of time stays the same, then it's okay. You don't have to convert. Okay, so there's actually two kind of rates that we want to talk about. We want to talk about average rate, and actually what I will say about average rate is this is kind of not chemically important, really. I mean, it's chemically relevant, but in terms of knowing what the average rate of a reaction is, it's really not chemically important. And so how do we find out what the average rate is? Well, we can use that formula, change in concentration of whatever it is over change in time. Or, and you'll see a lot of this throughout the kinetics unit, is we'll be able to talk, we want to talk about it graphically. Okay, so the second type of rate is kind of the more chemically relevant rate. This one's the more important rate, and this tells us how fast the reaction is going right now. Okay, like right this moment, how fast is the reaction going? Okay, and we usually use graphical means in order to solve for this. Okay, now, if anybody's taken calculus or knows anything about calculus, what we're trying to do is we're trying to find the slope of a curved line, because what happens as the concentration of the reactants changes over time, it's not a linear relationship, it's kind of a relationship that's curved. And so calculus is concerned with finding the slope of a curve at a given point. And so so to avoid having to do calculus, which, trust me, we can do kinetics based in calculus, but I don't want to, what we do is we graph the concentration over time, we find whatever point it is, we make a tangent line, and then we calculate kind of old school, find the slope of that line, the change in y over the change in x, or rise over run. Okay, and that instantaneous rate, that'll tell us exactly what the rate is at that point. Okay, so in order to really visualize this, or to understand what this is, here's an explanation, or here's a real-life kind of idea, okay? And so I'm traveling in a car. I'm going from Philadelphia to my job in Collingswood, okay? And I look at my speedometer, okay? I'm on 676. I look at my speedometer, and it says that I'm going 63 miles an hour. Okay, right at that moment. Okay, it must not be rush hour. But what I know is when I drive from Philadelphia to Collingswood, I'm really only averaging 25 miles an hour. Okay, so the point is that instantaneous speed, the instantaneous rate, is telling you is looking down at the speedometer. Okay, so I look down at the speedometer, I see how fast I'm going right this second. Whereas the average speed is the speed that I'm averaging over the whole trip. So while my average speed may be, 25 miles an hour or 32 miles an hour, I am not traveling at 32 miles an hour the whole trip. It would be ridiculous for me to leave a parking lot going 32 miles an hour. I'm taking my life in my hands at that point. So my instantaneous speed will change because of conditions that are my traveling conditions. Just like a chemical reaction, the instantaneous rate will change because the conditions in a reaction are always changing. So here is the graphical, kind of the graphical method for determining average versus instantaneous rate. And so we want to know how we would calculate the average rate from 0 to 300 seconds. So here's 0 and here's 300 seconds. Well, if we're going to calculate the average rate, okay, the average rate of, now we're talking about the reaction, like its concentration in moles per liter per time, okay? So the average will be just draw a line and find the slope. That slope, okay, the rise over the run is going to give you the slope. The slope is going to be the average rate of change, okay? Now, the instantaneous rate of change, again, is at one specific point. Here, this average is over the lifetime of the reaction from 0 to 300 seconds. Okay, if we're going to try to find the instantaneous rate of change at 100, well, there's the point at 100. So now I'm going to draw a tangent line there and then find the slope of that tangent line. Okay, and so those two values are going to differ because of how we figured them out. Okay, so the instantaneous rate of change is in the red here. Okay, the average rate of change is black over the whole distance. Okay. Now, lastly, the thing that I want to make sure we talk about is relative rates. How quickly does a reaction or does a reactant get used up versus the product? Okay. Sorry, I'm looking around to see what time it is. Okay. So, well, so we're trying to relate how fast something is going. So here's what we're going to do. We're going to relate how fast NOCl disappears, because what happens to the reactant is going to decrease compared to how much this is going to appear. So what is the mole ratio of this to this? The mole ratio is 1 to 1. Well, if the mole ratio is 1 to 1, the rate of disappearance, okay, so let's see if I can do this. The rate of disappearance of NOCl is going to equal the rate, capital R, of appearance of NO, because it's a 1-to-1 ratio. Now, when we compare this to this, what's this ratio? This ratio is 2 to 1 now. So that means this is going to disappear twice as fast as this is going to appear. For every 2 of these, we only make 1 of those. So the rate of appearance of this is half as much as the rate of disappearance of this, or this rate is twice as quick as the rate of appearance here. Okay, and so that's relative rates. Okay, so that kind of introduces you to the idea of rates, relative rates, instantaneous rate, average rate, and so we're going to move on from here in the next video and learn about some of the more detailed and fun stuff with kinetics.